u-substitution. So when we did differentiation, stop it. When we did differentiation, there were some rules. There was the product rule and the quotient rule and all that stuff. We learned some rules. But it was like a handful of rules, wasn't it? In integration, you just saw the table of integrals. It's almost like they're not rules. It's almost like they're solutions.
Yeah.
You know, so I don't know if there's like really rules, but there are techniques to integrate. And so u-substitution is a technique that is useful for many different problems where you're trying to integrate. You're like, how are we going to do this? There's not necessarily a rule, but there's a technique. So let me throw an example up here. We're going to do the integral of 2x plus 1 multiplied by e to the x squared plus x with respect to x. Right, so you look at this and you're like, well dang, if we were doing a derivative, wouldn't it be nice? We got a power, we have a product rule and an exponential rule with a chain rule with the power rule in the mix. And I guess that sounds kind of like a lot, but you could do it because you have rules. Yeah? Right. Autumn, you with me? That face. Taking the derivative, there's rules for this. Like this is a product of two functions, and then there's a function inside of a function. We have e to the stuff. Whenever you have to the stuff, there's a chain rule. So there's like rules for that. Anyway, right now we don't have a rule. However, does anyone notice anything in particular about, say, this here and that there?
Yeah.
Yeah, they look like they're related by, one is the derivative of the other one. And so u-substitution is a method of trying to be clever and look for if you can find a thing and its derivative within the integral. And if you can, then you will set u equal to the thing. U is the thing, and then you're going to do a du is its derivative. And then you substitute. So in this case, what's the thing?
X squared plus x, yeah.
Yeah, we'll say u is x squared plus x. And then if we take the derivative of both sides of this, right, we're going to ddx on both of these, we'll get the derivative of u with respect to x is what? 2x plus 1. And I know it's super confusing when I'm like, yeah, let's just move the dx to the other side, because I told you it's not a variable. They call these, the du, they call it a differential, so it's like an infinitesimal kind of small change in u with respect to a small change in x. So it's more like a concept. However, if you treat it like a fraction, you get good results, right? And it just works out. And there's probably someone way smarter than me who can do a better explanation of that. But
could you just like think of it as a unit?
Yeah.
And you can move units around.
I dig you right now. Yeah, treat it like a unit. So we'll multiply both sides by the unit of dx. It kind of is a unit. It's a change in x. So if we multiply both sides by that, du is all that dx. And so now we have u is equivalent to this stuff, and du is equivalent to this stuff. So I can go back to this integral that I don't have a chance of solving, because right, I mean, look at that. That's saying, what's the thing that when you take the derivative of it, you get this?
Yeah.
I'm not going to do that.
Yeah.
Right? Like I can feel my cerebellum starting to drip out of my nose just thinking about it. But if I say, hey, x squared plus x, I know you. I know you. You see what I did there? So this is going to be, there's going to be some stuff and then there's going to be an e to the u. Autumn, you with me? We substituted the u.
Yeah.
Oh yeah, can we close that?
Ew.
Bless you. I felt like I missed off of that one. That was a good spread.
Ew.
Okay, and now 2x plus 1 dx. That's up here, right? That's all this. Yeah. And so I could replace all this with what? du. So I'm going to replace all that with du. Yo, look at that integral. That integral is so lovely right now. The integral of e to the u with respect to e. Come on. Come on. You want to do that. Right? I know you want to do it.
E to the u.
Yeah. It's e to the u. Rocket surgery.
Why? Because the derivative of e is.
And then e to the x squared plus x.
Yeah.
Oh, wait. What?
The derivative of e to the x is e to the x, right?
Yes.
Yeah. So the derivative of e to the u is e to the u. I mean, we can
Okay.
we can do that.
Okay.
Say what?
That's some wizardry.
It is. It is. But now we say, oh, hey, we better put that back where it came from. So that's not a u. That's x squared plus x. And so if I were to say, hey, you guys, take the derivative of e to the x squared plus x plus 5.
It would be.
So remember, the derivative, we're going to take a walk down memory lane. This is
Yeah.
pre-spring break,
Could be e to the
which
x.
is eons ago. But the derivative of e to the stuff
Yeah, it's e to the
is
stuff.
e to the stuff.
And then chain rule.
And then chain rule, you multiply by the derivative of stuff.
Yeah,
Times
2x.
And the derivative of 5 is 0.
Yeah.
So it worked. It did.
Yeah.
You can say, oh, all you want. It worked. So u-substitution is pretty slick. And I mean, it doesn't work all the time, obviously, because there's not always a thing and its derivative at the same party. Hey, fancy seeing you here. But it happens often, especially with trig functions, because they're all derivatives of each other. They're all, you know, inbred weirdos. Let's try it. Right? Hey, I know you. Because the sine, right, the derivative of sine is cosine, the derivative of cosine is negative sine. And if you take the derivative 2 more times, you get sine. So sine is its own great-great-grandfather. Something like that. It's nasty. Okay, let's try another example. Oh, and today is this day. Alright, so let's take the integral of 6x squared over 2x cubed plus 1 with respect to x. So u is going to be the thing, and du is going to be the derivative of the thing.
Is 2x to the third.
Can we throw in the plus 1?
Yeah.
And du
Is 6x squared. Yeah.
Alright, we'll pump the brakes a little bit. You notice how there's a thing, and then if you take the derivative of this thing, you get that thing?
So
The derivative, so you gotta remember your differentiation skills.
Ah, I got that.
Yeah, multiply this by this, and then you drop it squared. Yeah. And the derivative of 1 is nada. So anyway, we can substitute. Serge, you want to substitute for us?
I'm good.
I'm all set. You can do it. I believe in you.
Go ahead and done.
Were you waiting for him?
Yeah.
I'm
du
sorry.
over dx.
No.
No, what did you say?
Okay, cool.
Yeah, use your brain.
Um,
So where do you see the u? Where is that?
well,
Okay. And what's? Oh, I'm sorry. This du. If we do du dx, remember we multiplied and the dx is over
Wait,
here.
why can we do that though? Isn't that changing it? It's not like we're doing the same thing to both sides.
This thing?
Yeah.
Because we took the derivative of both sides. We did the derivative of this and the derivative of this. And so we get a du dx. And this ddx applies to that,
So
and we do the derivative.
Write them as they're related to each other.
So this is equal to that. And then we're going to move our unit over here.
Okay.
Right, Autumn?
Mm-hmm.
I know that's right. Okay, so, and Sergio, finish the job, Hefe. Yeah. So we can technically, we can put the du here, but that's confusing for some people. So we like to just put a placeholder there. And it's always good to put the dx or the du or whatever at the end of your integral. Because you're saying blah, blah, blah with respect to u.
That doesn't make sense.
What happens to the dx then?
Okay, hang on. We have
That's
a code blue. So this is du, correct?
Yeah.
Okay, so
Right. Yeah.
so you're cool with that.
Yeah.
And now I'm just saying we can put the du over here and just put a 1 here as a placeholder. Because I can. You can't stop me. Right, it's like if we have 7, 6, that's the same thing as 1/6 times 7. Feel me? Wait, we're just Rubik's cubing it around. Yeah? Okay. And now, the integral of 1 over u,
natural log u.
natural log of u. Natural log of u, and then our constant of integration. But let's go ahead and plug that u in there. Natural log of
2x.
and I feel like they always do absolute value because you can't take the log of a negative or a 0.
what did we plus c?
Yes. Good eye, Chief. There's always that constant of integration. And now you might be able to look at it with your brain and say, hey, if I did the derivative of natural log of stuff, it's 1 over stuff times derivative of stuff. So we would get 1 over this times the derivative of that. See how we just inside outed it? We're doing it backwards?
Yeah. For sure.
Yeah? Alright. Uno más. Yeah. This one's not super
Yeah, exactly.
obvious. What happened?
Safe.
Okay, we'll do the integral of the square root of 3x plus 5 with respect to x. And now you're like, what?
3x plus 5 all to the 1/2. Yeah.
Alright, we can do that. This is the integral of 3x plus 5 to the half. And now if we were taking the derivative, there's a chain rule happening.
Why?
If we were taking the derivative, this is stuff to the half.
Okay.
Whenever you say the word
Right,
stuff,
stuff.
it's a chain rule.
True.
So we would do, you break down the half and then drop the exponent and then multiply by the derivative of stuff.
Ugh.
So in this case, I mean, the only thing that this could be would be 3x plus 5.
Mm-hmm.
So let's try that. We'll just walk down that road, see what happens. So what would the derivative of that be?
3.
I forgot.
3 dx.
3 dx. So the integral, it's going to be, what's this going to be? U to the half?
Yeah.
Is that a thing? Okay, u to the half. And now this dx,
Multiplied by 3. I don't know.
how about let's find out what dx is equal to. dx is that, isn't it?
Yeah.
Okay. So let's replace dx.
What is du? Yeah.
So again, we're treating it like it's a thing.
Yeah.
It's kind of a mind.
But why does
Bible.
that make it better for us?
So, well, that makes u to the 1/2 over 3 equal to, or du.
So now we can replace dx with a third du.
Okay.
In which case, a third, it's just a number, and we can put that number out here,
Mm-hmm.
right? Because that number doesn't really change anything; it's just a coefficient.
Mm-hmm.
Autumn hates that, but these are the facts of life, my dear. So are we okay?
Yeah,
There's a lot of smoke and mirrors. Like, welcome to calculus. We're not in Kansas anymore. It's exciting stuff. But so now we can do the integral of u to the half, and remember we better leave a 1/3 out front. But Jason, will you take us on a ride?
equals 2 halves u to the 3 halves.
Hold on, let's start with the u to the what?
3 over 2.
U to the 3/2. And then what do you do with that? Okay.
Yeah. 2 thirds, yeah.
And then we're just, this guy's a tag along. Plus c. So we can simplify. What do we got? 2/9? 2/9
And
times what?
3x plus 5.
Yeah, now we can plug the u back in.
Ready? How do you do it tonight?
Huh?
1/3 times 2 thirds.
Oh,
Yeah, I'm just multiplying these guys. Now u is this.
To the 2 thirds.
Raised to
Three
3
halves.
halves. Plus some arbitrary number. U-substitution, ladies and gentlemen.